Yeah, thank you. Alright, so good afternoon everyone. Let's continue what we were trying last time. Right, so I'll just do a quick recap. We have already observed this, right? We observed this quite easily. In fact, we observed something much more general. In any matching chord graph, you look at a vertex of degree D and you consider the minimal classes, or a minimal class, induced by each of the edges incident at that vertex. Right? Then what you will get is D many minimal classes that are mutually exclusive. In particular, they are distinct pairwise. And of course, if you apply this to a brick, you get, at a vertex of maximum degree, you get delta many pairwise mutually exclusive minimal classes, but every minimal class is a removable class. Therefore, you get delta many removable classes. Bricks have minimum degree 3, so at least 3 removable classes in every brick. Right? And of course, what we really would like is to get the existence of a removable edge as a first step. Ideally, we want B inherent edge, but that is much harder. That is done in part 2 of the book. Right? So how do we go from delta many removable classes to at least one removable edge? Okay, so the problem is, what if all the delta happen to be removable doubletons? Well, since delta is at least 3, it means that you have at least 3 removable doubletons, and they are all pairwise mutually exclusive. Turns out that is actually very restrictive. It happens only in 2 graphs, K4 and prism, amongst the simple bricks. Right? So that's what we'll prove. We'll prove that a simple brick has 3 pairwise mutually exclusive doubletons. So we are going to relax the definition. We don't care whether the doubleton is removable or not. We just want equivalence classes of cardinality too. Right? So if there are 3 pairwise mutually exclusive doubletons, we will prove that the graph is either K4 or prism. Right? And for that, what we first did is we considered a pair of doubletons and tried to observe information like from that what we get. Right? So we took any 2 doubletons. For most of the proof, we did not actually care about this mutually exclusive part. So I'll just recall what we did. The first thing we observed was we have this very nice drawing. These are equicardinal. And the edges of Qi, so let's say Qi is Ei, Fi. Then 2 of the edges look like this, and the other 2 edges look like this. Let's say these are E1 and F1. Then these are E2 and F2. Their union is a 4-cut. And when you delete the 4 edges, you get 2 connected bipartite matchable graphs. Matchable is not too difficult to see. Just take a perfect matching that contains neither E1 nor E2. That's, yeah. In other words, you can delete E1 F1, and then you have a bipartite matching chord graph. Take a perfect or bipartite matchable graph at least. Yeah, but what if E2, F2 is using every perfect matching? Okay. Anyways, we didn't really use that fact, but we did observe that when you delete the 4 edges, you get bipartite components, and each of them is equicardinal. So the colored classes are equicardinal. Those things we observed. Okay. And then, of course, there are many ways to finish the proof from here. So until now, we have not used mutual exclusiveness. This is true for any 2 doubletons in a brick. This is what they look like, including K4 and prism. This is exactly what it looks like. Yeah. And now we assume that they are mutually exclusive, and we were able to observe more things. What we were able to observe is that if they are mutually exclusive, then actually this whole thing is a single vertex, and E1 and E2 are incident at the same vertex. and likewise this is a single vertex, and f1 and f2 are a single vertex. So in fact, in that case, what we get is something like this. Of course, the adjacency could happen either here or there. I'm just doing it without loss of generality. But there are edges here, and in fact the vertex has degree at least 3, so that means this is the situation. In fact, the degree is exactly 3 now, because there are no more edges that go from the left side to the right side. And what we have here is what they call an H configuration. So what is an H configuration? Well, it looks like an H, if you draw it like an H. Oh, maybe I should not draw these. Hanging edges, right? H for hanging. So these are my E1 and F1, and these are E2 and F2. This is what it looks like. Yeah, and the additional condition, this is a degree 3 vertex, this is the degree 3 vertex, and there is this edge that is conveniently called little h. Yeah, so this is the situation. Yeah. So the point is that if they are mutually exclusive, then actually they must induce, this is the terminology they use, they must induce an H configuration. And of course, if they induce an H configuration, then of course they are mutually exclusive. So therefore it is if and only if. They are mutually exclusive if and only if Q1 and Q2 induce an H configuration. Yeah, we literally spell out H. Yeah, and this is the H configuration. And observe that I have deliberately not drawn the vertices because I really do not know how many of these are distinct vertices. In K4 you have H configuration, it's just that there are 4 vertices. So H configuration doesn't tell you that the graph has at least 6 vertices. Yeah. Alright. So now we have a proof of this. I think we covered almost all the details last time, if I'm not mistaken. Right? I just did not have enough time to define H configuration, or if I did, I forgot. Yeah. Okay, so that's done. And now let us use this to observe this. Yeah. Now I have Q1, Q2 and Q3. They are pairwise mutually exclusive doubletons. So I can apply this lemma for each pair. If I apply this lemma for Q1 and Q2, maybe I'll draw the H like an inverted H now. This is my, I don't know, this is my edge E1, this is my edge F1. So this is not F1, this is E2, this is F1, this is F2. Right? I have applied it to Q1 and Q2. And Q3 is the third doubleton, E3, F3. Right? But now I can also apply the lemma to Q1 and Q3, or Q2 and Q3, and so on. Yeah, let's see what happens. Supposing I apply it to Q1 and Q3. That means for Q1 and Q3, the edge E1 should have a common end with either E3 or with F3. Yeah, E1 has a common end with E3 or F3. So that means that this edge here is either E3 or F3. Is that right? Maybe not. No, the common end need not be this. The common end need not be this fellow, the common end could be this fellow as well. Yeah, so those are two possibilities. Either this is E3 or F3. Okay, so those are the two possibilities. Either the H edge, either H is in this set or H is not in this set. Yeah, okay. Let's suppose H is in this set. This is E1, E2, F1, F2. If H is here, then this is either E3 or F3. So let me put it as E3. Yeah. Now E1 has a common end with E3. Therefore, F1 better have a common end with F3. Yeah. They better form the H configuration. So that means that F3 is incident at this vertex. Yeah? Maybe I'll just put a vertex. F3 is actually incident here. Yeah? Now let's look at 2 and 3. F3 should have a common end with E2 or with E3. With E3 it cannot have a common end because I already have 3 edges here and I already have 3 edges here. F3 is an edge that is none of these 5 edges. Therefore, the common end of F3 with E2 has to be this vertex. Yeah, and that basically means that E2 actually goes like this. Wait a second. E2 is this edge and F3 is this edge. Yeah, and at this point there is enough information to just finish the graph, and this is K4. There are multiple ways to finish this also actually. If you want, you can draw this triangle. This is E2, E3 and F1. Yeah. Observe that what are these edges? The common edge coming out here is E1. The common edge coming out here is at E2 and F1, it's F3. And the common edge coming out at E3 and F1 is F2. It's a brick. This can't be a tight cut. There should be a perfect matching containing all 3 edges. Unless it is trivial. You can't have a perfect matching containing F3, F2 and E1. That should also contain E1, E2 and E3 because these are doubletons. So therefore, it can't be non-trivial. There is a single vertex outside and all 3 edges are going here. That's K4. Right, so anyway, there are multiple ways of finishing this point. I think you all can try it yourself as well. And I was able to do it at least in 2 or 3 different ways while I was trying it out. Right. So there is enough information in this lemma to basically settle this. Let's consider the case where H is not E3 or F3. Well, if H is not E3 or F3, but E3 and F3 need to have common ends with E1 and E2, the only possibility is it like this. E3 or F3 has to be like this. And if H is not E3 or F3, then by symmetry, E3 or F3 has to be like, the other edge has to be like this. And if you want the edge configuration, the only way is this. Did I make a mistake in the labeling? E1 F1 is a doubleton, E2 F2 is a doubleton, E3 F3 is a doubleton. Yeah, that's fine. Yeah. So I would suggest that you all try this out in case you haven't already. It's really not that difficult. Once you have this lemma, you actually have everything you need. You just have to apply the edge configuration lemma to all 3 pairs. And you just don't have enough space to make a bigger graph. Also because when the edge configuration happens, those 2 vertices become degree 3. Yeah. Okay. So that proves this. These are the only 2 simple bricks where you have 3 pairwise mutually exclusive doubletons. Therefore, it proves this. Every simple brick has at least max degree minus 2 removable edges, therefore at least 1 removable edge, except K4 and prism. Yeah? Okay. Yes. Any questions? No. Alright, so that's that. So what we have done is we have proved the existence of a removable edge in a brick, except K4 and prism. Yeah? Simple is of course not a big deal, because of course if you have a multiple edge is a removable edge, so that's fine. Right? Good. So the story that I've mentioned earlier is that this is something that was already there in Lovász's 1983 paper, which is I think the same paper we were discussing this morning. So this result is already there. It may not be in the same language. I'm not sure if Lovász used the term removable edge, but this is basically there. But one of the reasons Lovász was working on these topics was to solve the so-called matching lattice problem. That was the big open problem back then. And eventually Lovász solves it in 1987, which is the same paper where the unique tight-cut decomposition theorem is proved. The first theorem proved in that paper is the unique tight-cut decomposition theorem. Right? And in that paper, Lovász solves the matching lattice problem. The paper is called the matching structure in the matching lattice. Yeah, that's the order, I think. And Lovász makes this conjecture. I don't know if the conjecture is actually published, but it was a popular conjecture amongst the people who knew the topic, which is that now that you know that the tight-cut decomposition is unique, you can define a B invariant edge. Right? Now you can define the B invariant. Right? It's the number of bricks of a matching code graph. And now you can define a removable edge to be B invariant if B of G minus E is equal to B of G, where E is a removable edge. Right? And since the Peterson graph plays a special role in Lovász's characterization of the matching lattice, right? So the dimension of the matching lattice actually depends on not just B, number of bricks, but number of Peterson bricks. Right? So Lovász conjectured that actually all bricks except K4, prism and the Peterson graph, all simple bricks, I don't even need simple, yeah. All bricks except K4 and prism and Peterson graph, each of them has a B invariant edge. And this was the conjecture that Lovász had announced, and that is much harder to prove. That was eventually proved by Carvalho-Lucchesi-Murty. Lovász and Vempala announced the proof, but they never published it, and eventually Carvalho-Lucchesi-Murty published it. Their proof. But that is much harder, to the point where it is not even proved in the first part of the book. It is proved in the second part of the book. So the way they prove that conjecture, right? So maybe I'll just mention to motivate the next chapter. So the conjecture of Lovász was that every brick except K4, prism and the Peterson graph has a B invariant edge. B invariant is a removable edge E such that number of bricks does not change. So this is much harder, but what they did is they first proved it for solid bricks, which are the bricks that do not have non-trivial separating cuts, right? This was actually one paper in JCTB where they proved the conjecture for solid bricks. And then there was a second paper in JCTB by the same authors where they used the fact that it is true for solid bricks, develop more machinery and prove it for all bricks, right? So hence, the next chapter is on solid bricks. Okay. So it has a bunch of results all about solid bricks. Some of them are very technical and I still don't know how exactly they are used where. So I'll just present them as they are and I'll try to relate them to some things we have seen earlier to motivate them. Right? But before we go there, let me just conclude, let me say a few more things about this drawing. Right? So before we go to solid bricks chapter, observe that this is what two doubletons look like. You may ask, what do k doubletons look like? Well, look, that there is a very nice drawing of C6 bar. This is the triangular prism. This is one removable doubleton. This is the second removable doubleton. And this is the third removable doubleton. Turns out this is not a coincidence. In any brick except K4, K doubletons, I don't think you even need them to be removable. When we proved it in 2015, we thought we were assuming they are removable. Let me just check. It is one of the exercises in your assignment. Or they call it removable doubletons. Fine. Sure. So, while you are doing this exercise, think about whether you really need removable or not. I'm not too sure. If you have a brick with k removable doubletons, if you delete all the 2k edges, your graph will break into k many components. All of them will be bipartite. And the edges you deleted, they look exactly like this. This is R1, R2, R3, and if you want R4 or R0, whatever, I like 0. Yeah. These are your k removable doubletons, where k in this example is 4. You delete all the 2k edges, you'll just get a bunch of bipartite graphs. Each bipartite graph will definitely have equicardinal color classes. I believe these are also matchable, but I am not sure. You can check it in the exercise. But this is what it looks like. And so actually Marcelo and Claudia had come to Waterloo in 2014 and we sort of had figured out all this back then together. And I should have written up a paper and published it. We never did that. I never did that, more importantly. So it was never published. But in the book, they actually mentioned that this is a private communication between the 4 of us. But yeah, there is no paper to show for it. Yeah, eventually there was a paper by a few authors from China who proved a special case of this. I think they only proved it for cubic bricks, but the reality is it goes through for all bricks. But that was in the context of some conjecture we had. So they had the same thing but more restricted version. And you may ask, using this, can we get an upper bound on the number of removable doubletons? We can, right? The upper bound is the extreme case is achieved when this is just single vertex, and so on. When each of these is K2, that is when you have the maximum number of removable doubletons with respect to n. So for any k removable doubletons, I can get this drawing. Therefore, I can get it for all the removable doubletons together. And therefore, the maximum number of removable doubletons are precisely these graphs. and this is either a Mobius ladder or a prism, right? Yeah, depending on the parity, whatever. Right. So these are exactly, yeah. Right. So in fact, the result says that any brick has at most n over 2 removable doubletons, and equality is achieved if and only if the graph is either a prism or a Mobius ladder. The only exception to all of this is K4. K4 has 3 removable doubletons. N by 2 is 2. Okay. And if you delete all the removable doubleton edges in K4, then you just have 4 isolated vertices. Right. Whereas here you actually get bipartite graphs with equicardinal color classes. So yeah, so K4 is an exception. Anyways, so this is part of your assignment. And the chapter 9, which is what we are currently doing, has a section on near bipartite bricks. Yeah, maybe I should say a few more things that are interesting. Yeah. So one of the results that they prove is that if you look at simple near bipartite bricks, then you can actually prove the existence of 2 non-adjacent removable edges, except for K4, prism and bicon. In any simple near bipartite brick, except K4, prism and the bicon is this fellow. This is the unique removable edge, which also happens to be B invariant. And apart from K4, prism and this fellow, you will always find 2 non-adjacent removable edges in any near bipartite brick. Yeah. But anyways, I'll skip this. I'm skipping the whole section basically. They have marked it as this sharp symbol, so I was going to skip it. It's probably used in specific parts of the book. Yeah. I want to mention one more interesting connection with B invariant edges, which is something I've been discussing with Shalu recently. In the case of near bipartite bricks, you can actually define a special type of B invariant edge, which is what I want to tell you about briefly. So, if G is a near bipartite brick, recall near bipartite means there exists a removable doubleton. So let me fix a removable doubleton R. The removable word is important here, right? I'm not just considering a doubleton. So I have a near bipartite brick that has a removable doubleton. So let's say we want to prove the existence of a B invariant edge in these graphs. Again, we can't have K4 or prism because they don't even have removable edges, so they can't have B invariant edges. The problem is B invariance is not actually very easy to work with, as you will realize as and when you start working on it. Right? Some of you already are. So B invariance is nasty. But here is something you can do in the case of near bipartite graphs, or in the case of near bipartite bricks, for example. So let's say H is the underlying bipartite graph with respect to this fixed removable doubleton. Here is what is interesting. H is bipartite matching covered, right? Because it is a removable doubleton. Note that H is a bipartite matching covered graph. Let me make a figure. This is what H looks like. And if you put these two edges back, this is what G looks like. I like to use alpha and beta for the edges of R so that I can use E and F for other edges. Now here's what is interesting. You can take a removable edge in H, but that may not be removable in G. And you can take a removable edge in G, but that may not be removable in H. All of these are possible. What would be nice is if you could have an edge that is removable in both G and H. Why is it nice? I'll tell you. Supposing E is removable, in G as well as in H, then actually it is not too difficult to prove that it is a B invariant edge. This implies that E is B invariant in G. Of course, in the bipartite graph it is B invariant, because in a bipartite matching coded graph every removable edge is B invariant. What is interesting is that such edges that are removable in G as well as the underlying bipartite graph with respect to any fixed removable doubleton R, they are actually B invariant in the big graph G. And proving the existence of such edges is relatively easier. You don't actually have to compute the number of bricks in some sense. You just have to guarantee that the removable edge in G is also removable in the bipartite graph. That's the one way to think about it, right? And removability in bipartite graphs, we understand it much better than removability in life, right? So that's sort of the motivation for studying these kind of edges. The fact that every near bipartite brick except K4 and prism has such an edge was proved in CLM 99. So CLM 99, which is the same paper where dependence and all that was discussed extensively, there they showed that except for K4 and prism, let's take an example. Let's take the bicon, which I erase conveniently, of course. Inconveniently. Anyways, here is the bicon. This is my edge E. There are two removable doubletons, alpha, beta, call this R, and alpha prime, beta prime, call this R prime. Yeah? This edge E is actually removable in all three graphs. It is removable in G, it is removable in G minus R, it is removable in G minus R prime. That is actually easy to see because G minus R and G minus R prime are symmetric. Right? So this is an edge that I call R compatible as well as R prime compatible. So this is my definition for R compatible edges, where R is a fixed removable doubleton. So I mean a edge that is removable in G but also in G minus R. Those are called R compatible edges and they are B invariant. You may ask, oh, are all B invariant edges in near bipartite bricks R compatible for some R? Answer is no. There are B invariant edges in near bipartite bricks that are not compatible with any of the removable doubletons. And there are also cases where you have a removable doubleton R and the edge is compatible with this R but not with another R prime. Those things are also possible. Right? So all sorts of things are possible, but this is really nice. And R compatible edges are always B invariant. Of course, if I don't care about the R, I just care to be compatible with some removable doubleton, I just call them compatible edges. Compatible means R compatible for some R. Okay? So this is much easier to deal with, and if you are working on near bipartite graphs, maybe R compatible edges is the way to go rather than B invariant edges. Right? And the reason I wanted to mention this is one, because I discussed with Charu recently, two, because this is actually the second half of my thesis. The second half of my PhD thesis is basically about R compatibility. So that's one point I wanted to mention. Yeah. Another quick point I want to mention, this is also on your assignment. Near bipartite graphs, and this is a really unfortunate terminology, are near bricks. Have I defined a near brick before? A near brick is a matching code graph whose B is equal to 1. A near brick is any matching covered graph G with B of G equal to 1. So near bipartite implies near brick. Every near bipartite graph has exactly one brick, and that brick is actually also near bipartite. It will also have a removable of it, right? Yeah. But near bricks need not be near bipartite. Peterson graph, every brick is a near brick. Therefore, Peterson graph is a near brick. But Peterson graph is not near bipartite. Yeah? Okay. And the reason this terminology is really strange is because bricks are near bricks, but bipartite graphs are not near bipartite. Don't throw a rock at me. Okay. Fine. But yeah, anyway, there's a lot of confusion. But yeah, you just need to pay attention to the details, right? So the terms are a bit similar, but that's just, yeah. Okay. So that's all for this chapter. We are done with chapter 9, and we can move on to the next chapter, which is going to focus on solid bricks. It has a bunch of very technical results, and we will see some of them. Yeah, let's maybe take a break. Yeah, let's take a break. Are there any questions or concerns regarding anything we've discussed so far? Yeah, all good? Okay, so we'll meet in again 5-10 minutes.